So induction is a method of proving statements that are defined on numbers that have a clear succession, well, defined over. So let's, for example, say we want to prove that when we have 5 train stations, yeah, so those are my train stations, or maybe let me just kind of copy those. It's going to be definitely more convenient than drawing all of those. Yeah. So we've got, let's say, 5 train stations. And we'd like to prove that whenever we go to each one of them, we're going to find an orange waiting for us there. Okay, so how are we supposed to prove it? Well, for example, we could just go on to each one of those stations, we could get off the train there, and we could check if there is an orange waiting for us there. However, well, now, yeah, it is a reasonable thing to do because we have only 5 stations. However, what if we had 1,000,000 train stations? That would be, well, pretty time consuming, at least, yeah? So there is a better method for solving this kind of problem. So what we'd like to do is, first of all, we would like to go to the first station, that's the second station, that's the third, the fourth and the fifth station. We would like to go to the first station and check whether there will be an orange waiting for us. Let's say there is. Yeah, let's say it's checked. Awesome. So now what we would like to do is we would like to assume that there will be a station. Let's say it's going to be the cave station, such that if we go to that station and we get off the train there will be an orange waiting for us. And the cave station might be just about any station there is. So it doesn't really matter, we just assume there will exist some kind of a station, so we don't really know which one it will be. Yeah, awesome. And now what we would like to do is, after assuming this thing, we would like to prove that the fact that there will be an orange waiting for us on the cave station will imply that there will be an orange waiting for us on the station that is consecutive to K, so on the K plus first station. And you see, if we manage to prove that, we will actually prove that there will be an orange waiting for us on every single one of those stations. And well, why is it so? Because see, we checked by hand, by getting off the train, that there will be an orange waiting for us on the first station. And we know, because we proved it right here, that whenever there is an orange waiting for us on one station, there will be an orange waiting for us on another station, on the next station. What does it mean? It means that if there is an orange waiting for us on the first station, there will be an orange waiting for us on the second station. And that will also imply that there will be an orange waiting for us on the third station. And this means there will be an orange on the fourth station and the fifth station. We can just, go on indefinitely to prove it for just about as many stations as we would like to. And this is so-called induction. So let's maybe right now try and see what types of induction are there in this beautiful world. So, mate, would you mind, please? Of course, mate, I'm always here for you. Okay, guys, so what kinds of induction are there? So first of all, let's cover the type of induction Jerzy just talked about with this beautiful train station example he came up with. So, it was the so-called weak induction. So, weak induction principle consists of, conducting a proof using the weak induction principle consists of 3 steps we have to do. So first we have to achieve the base case scenario. So the base case is going to be the case on which we're going to be building our problem-proving sim-improving machine. So basically just going to the first station and checking whether there will be an orange waiting for us. Yeah, so what we do then is we do the assumption. We make an assumption. So the assumption is that we will basically just assume that there will be a number in the set we are trying to prove this statement on, that our statement will hold for that number. So we will just assume that there will be a train station such that on that train station there will be an orange waiting for us. And then the third step we have to conduct is the inductive step. The inductive or induction step, I like to call those ones. I like to call this one One of those two, yeah. So the inductive step basically is just proving that the fact that our statement will hold for the number k will mean that it will also hold for the number consecutive to k, so for k plus 1. This means that we will just prove that if there will be an orange waiting for us on the first station, there will be also an orange waiting for us on the second station. Yeah, and so that is the weak induction, because now we can just go on and apply the inductive step to the base case we made at the very beginning, meaning that, well, the number consecutive to the base case will also hold the statement, and every single number after that will also be true. I mean, the statement will hold for also that number. So now the strong induction. Strong induction is basically just kind of a weak induction. However, this time what we're going to do is we're going to check a few base cases. And what you're going to see in a few seconds. So the second thing we do is we make an assumption. However, this time the assumption is going to be a little bit different. So this time we're going to assume that the statement will not hold for a particular k. We're going to assume that it's going to hold for all of the values of k that are between the base case number. So the base case is going to be less than or equal to n, that is going to be less than or equal to k. So I should have actually written assumption first. Okay, so assumption. So assume that our statement will hold for all of the values of n, so all of the values of the number that our statement is defined on between the numbers of the base case we achieved and k. Well, that actually kind of shows us why we had to do at least two of those base cases. Yeah, so greater than or equal to 2, yeah, I mean, or maybe at least 2. Let's say, because at least 2 cases. Because if we're going to assume our statement for more than one number, we also have to prove it for at least 2 numbers for our proof to make any sense. And then we do the inductive step, which is the same thing as we did earlier, which is just, well, we use the assumption we made to prove that our statement will hold also for the number that is consecutive to k. So if we were to say how it works in terms of the beautiful example with trains and stations and oranges, well, we just check on the first 2 stations whether there will be an orange waiting for us. We assume that there will be an orange waiting for us on every single station, that is up to a particular station we choose. And what we do then is we use that assumption to prove that there will be an orange waiting for us on, well, station that is consecutive to the last station we assumed it for. Yeah, so that will also mean that there will be an orange waiting for us on every single station we go to if we manage to prove something like this. And now the third and the last type of induction we're going to be covering today, which is the Cauchy induction. The Cauchy induction works kind of interestingly because it has a fixed base case. So as in other examples, if we were, for example, dealing with negative numbers and wanted to prove some kind of statement only for the negative integers, yeah, then our base case would probably be -1. And then we would prove that our statement, assuming it will hold for some, let's say k, will also hold for k minus 1. This way we can just go on through all of the negative integers. However, this time we have a fixed base case, and it's fixed for n always being equal to 2. Why is it so? Wait a second. So now we do an assumption. We assume that our statement will hold for k. Assume holds for k. That's it. Now we do the inductive step. So the inductive step is going to look something like this. It's actually going to be pretty interesting. So we prove that our statement holding for k will imply the statement holding for double the k, which will prove that our statement, the original statement, will hold for every single power of 2. I mean, provided our base case was n is equal to 2. However, well, this is not quite enough because nobody in their right mind would like to only prove the statement for powers of 2. I mean, maybe some particular statement, but not most of those, yeah? So now we would like to conduct a second inductive step, so the step number 4, Yeah, so the second step is the step number 4. So the inductive step. I forgot to write step here. Inductive step, inductive step. That's gonna be that we will prove that our segment holding for k will also imply the segment holding for k minus 1. And what does it mean? Well, it means that now if the segment holds for k, it will hold for 2 times k, but if it holds for 2 times k, it will also hold for 2 times k minus 1. What does it mean? Well, it means that we just proved our statement for all of the even numbers and all of the odd numbers. Well, all of the odd integers and all of the even integers is all of the integers. Huh? That's a pretty interesting thing. I mean, apart from 1, because our base case is greater than 1, so yeah, that's that thing. Okay, so those are types of induction, and I don't know how about you, but I think it's a good moment to do some problems. Okay guys, so maybe now we would like to try and solve something using induction. What would you say about that? So, what I would like to propose you guys to solve right now is, we would like to prove that the sum of all of the consecutive integers from 1 to n is going to be always equal to n multiplied by n plus 1 all over 2 for every single natural number n. We would like to prove that one by induction. Awesome. So, let's try and first of all achieve the base case for this problem. So, what's going to be the base case scenario for this problem? We're dealing only with natural numbers, and so what will be the base case when we're dealing with natural numbers? Well, there's going to be the least natural number there is, and that is, you guessed it, 1. Perfect. I mean, at least in this case, it's going to be for sure 1, but sometimes we will debate whether 0 is a natural number, but this time it doesn't really make any sense because we're summing up numbers from 1 to and some from 1 to 0 is whatever. So base case is going to be n is equal to 1 in this particular nice case. Awesome. So for the n equal to 1 case, what are we going to get? Well, the sum from 1 to 1 is just 1. Awesome. We don't really sum up any order, any other numbers apart from 1 right there. And it's only 1 from 1 to 1. Okay, whatever. So 1 is going to be equal to, I mean, hopefully it's going to be equal to, well, 1 multiplied by 1 plus 1, which is 2 all over 2. So that's going to be 1 is equal to 1. Perfect. That's exactly what we wanted to derive from the base case. I mean, we know that it's true. Awesome. Perfect. So now, we would like to assume that there will exist some kind of a natural number, let's call it k maybe, such that our statement will hold for k. Perfect. So, we would like to assume there's a natural number k such that the sum from 1 up to k of all of the consecutive natural numbers is going to be equal to k multiplied by k plus 1 all over 2. Lovely. And now the induction steps. So we would like to try and use what we just assumed right there with that nice k to prove that the sum of all of the consecutive integers from 1 up to k plus 1, so the next number, the number consecutive to k on the number line, is going to be equal to k plus 1 multiplied by k plus 2 all over 2. You see what I did there? I just kind of plugged in k plus 1 for the nice expression we had there in the problem statement. Yeah, awesome. So what we would like to do now is, well, find a way to use our inductive assumption to help us solve this bit right there, because honestly, without using it, it's going to be probably pretty hard to solve it in most cases. So, well, how can we apply our induction assumption here? Well, you see this bit I'm highlighting right over there, so the sum of all the integers from 1 up to k by our inductive assumption is going to be equal to k multiplied by k plus 1 over 2. That's a nice thing to do. So I mean, plugging it into our equation is a nice thing to do. So we're gonna just go on and do it. So this, this equality right there is gonna become k k multiplied by k plus 1 all over 2. It reminds you that's what the sum of all of the integers from 1 up to k is gonna become, plus we will have to add that remaining k plus 1, which we didn't do anything with. Awesome. And that's supposedly equal to k plus 1 times k plus 2 all over 2. Perfect. So now let's maybe try and do something with that k plus 1 bit, because it's kind of just flying around and not doing anything. So let's try to get it to a common denominator with that k multiplied by k plus 1 thing. So what we're gonna get is k multiplied by k plus 1 all over 2, nothing changes here, plus getting the second parenthesis on the left hand side of the equation to a common denominator is 2 times k plus 1 all over a 2. That's supposedly equal to k plus 1 multiplied by k plus 2 all over 2. Perfect. So now, well, you see, I can just kind of take this k plus 1 factor out of this entire expression on the left hand side of the equal sign. So what I'm gonna be left with is k plus 1 multiplied by k plus 2, everything divided by 2. That's supposedly equal to, oh wait, well, it's not supposedly equal anymore, it's actually pretty surely equal to, well, k plus 1 times k plus 2 all over 2, which is itself. So yeah, we managed to get our original equality, sorry, that we had right over there in our induction step to, well, kind of like in form where it's, well, definitely obvious that it's true and there is no other way around it. It just has to be true because, well, a number has to be equal to itself. Which is absolutely perfect, because this will tell us, well, that our system was correct and that we did our induction proof the right way. Okay guys, so for the next problem we're going to be solving, we have something like this. We're supposed to prove that for all natural numbers greater than or equal to 1, all the n's that are greater than or equal to 1, we have the following equality holding right there. So, the following equality, what the hell with those inequalities today? So, following equality holding. Awesome. So that's going to be 1 minus a half plus a third minus a quarter plus ... So we're just kind of extending the alternating sum such that we are just kind of adding all of the fractions with an odd denominator and subtracting all of the fractions with an even denominator from that sum, up to 1 over 2 times n minus 1 minus 1 over 2 times n. Perfect. That would like, and we would like to prove that it's equal to 1 over n plus 1 plus 1 over n plus 2, and we're just going to be increasing that denominator by 1 until we get to 1 over n plus n, so 1 over 2 times n. That's lovely. Yeah, so we would like to prove it for all of the n's that are greater than or equal to 1 and are natural. So we would like to use, well, you guessed it, induction. So first of all, we have to consider the base case. What's going to be the base case in this scenario? Well, that's going to be the list number we're dealing with. So the list number we're dealing with is n equal to 1. So that's also going to be our base case. So n equal to 1 is the base case. Now, for n equal to 1, what are we going to get? Well, we're going to have the alternating sum become 1 minus, so 1 over 2 times 1 minus 1 is just a 1, minus 1 over 2 times 1 is a half, so it's going to be 1 minus a half. That's going to be equal to there's a girl who wanted to go by this tunnel, and so I'm recording, she just turned away. Oh, poor thing. Sorry. So and on the right hand side I'm going to get 1 over 1 plus 1, which, well, on both those hand sides are equal to a half right there. So we have our base case 100% holding. Awesome. So now we would like to assume, proszę bardzo. Now we'd like to assume that there will be a case such that 1 over a half plus a third minus a quarter plus ... 1 over 2 times k minus 1 minus 1 over 2 times k is equal to 1 over k plus 1 plus 1 over k plus 2, and we'll be just adding stuff up to 1 over 2 times k. This was not this girl, this was some really nice old lady. But she had more courage than the first one. Awesome. So now I would like to do the induction step. So that was our assumption. Now the induction step. So the essence of our proof. So the induction step. Perfect. So for the induction step, we would like to use our induction assumption we just made to prove that our statement will also hold for the number that is consecutive to k. Yeah? So we assume it for k, we would like to prove it for k plus 1 using the assumption that it holds for k. Lovely. So how our statement is going to look like for k plus 1, big D n. It's going to look like this: 1 over 1 minus a half plus a third minus a quarter, and it's going to be extending this alternating sum until we get to 1 over 2 times k plus 1 is 2 times k plus 2 minus a 1. That's going to be a 2k plus 1 and minus 1 over 2 times k plus 2. What about the sum on the right hand side? So how it's going to look like for k plus 1 being the n? It's going to be 1 over k plus 2. You see, it's not starting with k plus 1 anymore, it's starting with 1 over k plus 2, because, well, k became k plus 2, so that's the reason. Now 1 over k plus 3, and we're just going to be adding stuff until we get to 1 over 2 times k plus 2, which is absolutely perfect and lovely. So, now how can we use our induction assumption to try and help ourselves solve this problem, to help ourselves go on and prove this statement in the induction step? So, well, first of all, I would like to kind of rewrite both hands sides of this equality, and you're gonna see why in a moment. You're gonna see why I'm doing it, the reasoning behind this in a few seconds. So 1 minus a half plus a third minus a quarter, and now I would like to stop iterating on 1 over 2 times k minus 1 minus 1 over 2 times k, and now what are the only missing 2 terms of this sum right there? Well, those are those on the right hand side. So 1 over 2 times k plus 1 minus 1 over 2 times k plus 2. That's absolutely awesome. So now on the right hand side, what we're going to get is 1 over k plus 2 plus 1 over k plus 3 plus plus 1 over 2 times k plus 1 over 2 times k plus 1 and 1 over 2 times k plus 2. That's exactly what I want to hear. So now I would like to, for a moment, come back to the assumption we just made. So we see that the sum, that alternating sum from 1 minus a half to 1 over 2 times k minus 1 minus 1 over 2k is equal to 1 over k plus 1 plus 1 over 2 times k. Okay, that's pretty nice, because what we can, well, once again, do here is notice that we actually have those two sums on both hand sides kind of integrated in those, well, sums that we got after applying k plus 1 being equal to n. Yeah, so we see, maybe let's do it like this. So let's go back to our assumption. Sum on the left hand side I'm gonna denote as p, and the sum on the right hand side I'm gonna denote as, let's say, r. Yeah, r. Awesome, like a pirate is r. So now we see here that this stuff right there is actually equal to p. This 1 minus a half up to 1 over 2k minus 1 minus 1 over 2k. That's actually p. What about the right hand side? Oh my god. So what about the right hand side? We see that, well, this thing right there would actually have been equal to r if we had this 1 over k plus 1 term at the very beginning. So we can just kind of say that this thing right there is actually equal to r minus 1 over k plus 1. You following with me? I hope so, yeah. So now let's go on and rewrite the entire thing using what we just got as p which is p which we add 1 over 2 times k plus 1 and subtract 1 over 2 times k plus 2 from is equal to r minus 1 over k plus 1, which we add 1 over 2 times k plus 1, 2, and add 1 over 2 times k plus 2, 2. Awesome. So now we see by our assumption we made earlier that p is actually equal to r, which is, well, the inductive assumption we made earlier. So we can just go on and subtract those two from both sides of this equation, of both sides of this equality. So what we get is that we just can nicely go on and subtract p and r, being left with, what are we left with? We're left with 1 over 2k plus 1 minus 1 over 2k plus 2 is equal to negative k plus 1 over k plus 1 plus 1 over 2k plus 1 plus 1 over 2k plus 2. And, well, this actually is something that we can prove using algebraic manipulation. I mean, we can just kind of go on and, manipulate this all of those expressions a little bit, trying to get it to the form, well, both sides are equal to each other. Well, that's something which absolutely couldn't have done before we applied this inductive assumption we made earlier. So let's try and do it. So getting the left hand side of our equality to a common denominator, what we're getting is, well, we are getting 2k plus 2 minus 2k minus 1 all over the product of those two, so 2k plus 1 multiplied by 2k plus 2, which is perfect. So now, what are we getting on the right hand side? Well, that's gonna be a little bit more tough, honestly, but no. So we're gonna get 4k plus, I guess it's gonna be like 4k and 3, because, well, that's going to be 2k plus 2 plus 2k plus 1 all over 2k plus 1, 2k plus 2. Lovely. And now we have to subtract that 1 over k plus 1. So we're just going to kind of go on and rewrite the entire, left hand side right now. Nothing fancy here, nothing changing here. However, we will do some changes to the right hand side. So we unfortunately will have to do a little bit of, well, multiplication here, which I hate it. I hate well, explicitly working on numbers and letters is just so boring. So 4k plus 3 times k plus 1, that's going to be 4k squared plus 4k plus 3k plus 3 minus, it's going to be 2k plus 1 times 2k plus 2, that's going to be 4k got frozen there. So 4k squared plus 4k plus 2k. Yeah, that's 2k, and sorry, I should have put those minuses there. Yeah, awesome. And now we just kind of go on and divide everything by 2k plus 1 multiplied by 2k plus 2 by k plus 1, and what we actually get is that, well, this stuff here on the top side of the equation is gonna turn out to be equal to k plus 1, so we will just be able to nicely cancel out those two, being left with 1 over 2 times k plus 1 times 2 times k plus 2 being equal, well, quite nicely, honestly, to 2 times k plus 1 multiplied by 2 times k plus 2 on the right hand side. And so we see that those two are actually equal to each other, and we see that this is nothing else but the end of our proof, because we managed to show that those sums are indeed equal. Why we actually did show that those sums are indeed equal? Well, you see, we knew that before applying the assumption, before changing k to k plus 1, those sums were equal. Yeah, so then we kind of changed them. Yeah, so we subtracted something from the right hand side sum, and also something, and we also did add something to it, we also added some stuff to the sum on the left hand side, yeah? So we did change both of them, but actually we managed to prove that they changed by the same amount. And so if they were equal before and they also changed by the same amount, well, they had to remain equal. Yeah, you see, if I have 5 which is equal to a 5 and I add a 3 to both of those 5s, they both are equal to 8, so they are both still equal to each other. That's the end of this problem. And you know, let's do one more. Okay guys, so let's try and do another problem. So the third problem of today's video. We would like to solve the C1 problem from the 2014 IMO shortlist. So, let endpoints be given inside of rectangle R such that no two of them lie on a line parallel to one the size of R. The rectangle R is to be dissected into smaller rectangles with sides parallel to the size of R in such a way that none of these rectangles contains any of the given points in its interior. Prove that we have to dissect R into at least n+1 smaller rectangles to get the desired partition. Awesome. So what we are given here? We are given a rectangle which is called R and endpoints of it. No two of those points lie on a line that is parallel to the size of R, and also we know that none of these small rectangles that will have sides parallel to the size of R consist any of the points that we were given at the very beginning of the problem inside of it. What does it mean? Well, it means that each and every one of those points have to line, well, either on a crossing of sides, so at a vertex of one of those smaller rectangles, or maybe on the sides of those smaller rectangles. Right over there. Yeah, awesome. So, what does it mean? Well, no two of those points can line on a single line, so that means that, well, they cannot really line on a vertex, because a vertex is a crossing of two lines. So it means that each and every one of those points has to have its own unique line somewhere there that is also a side of a rectangle in order for us to get the desired partition. Awesome. So we want to prove that we have to partition our rectangle R into at least n+1 at least n+1 rectangles. Awesome. So we would like to maybe restate this a little bit. So I would like to denote the number of all of the rectangles in the after the partition as k. Yeah, so k is going to be the number of all the rectangles, and we want to prove that it's going to be greater than or equal to, so it's going to be at least n+1, which is the number of all the points, plus a 1. So also restating it is k minus 1 is going to be greater than or equal to n. This is actually the same we would like to prove using induction in this problem. Awesome, so let's first of all try and achieve the base case for this scenario. So the base case is going to be for k, which is equal to 1. So we are given only one rectangle. What does it mean that we are given only one rectangle? Well, it means that we are only given the rectangle R, and well, since points inside of R can't really lie on sides of R or anything like that, we have that they can't lie in its interior and they can't lie on its sides, they just can't really lie inside of R. So we are given that there are n is equal to 0 points, and we definitely see that k minus 1 is greater than or equal to 0, because 1 minus 1 is greater than or equal to 0, because 1 minus 1 is 0 and 0 is equal to 0. Awesome. So now let's try and do our inductive assumption. Yeah, so assumption. Lovely. So for our assumption, we would like to assume that there will be some kind of a k, yes, some kind of a that for some k, let's say, we're gonna have that for a partition of some kind of rectangle into k rectangles, there will be at most k minus 1 points inside of that rectangle. And now let's use the assumption to prove our prove the statement in our inductive step. Yes, so inductive step. So we'd like to actually conduct a pretty neat trick kind of a proof here. So we are given a rectangle, maybe let me prolong it a little bit, and so we will just partition it as an example in some way that is given in our problem statement. Yeah, so something like this, maybe something like that. Well, that pretty much covers it. Yeah, so we see that our entire rectangle is partitioned using lines that go from one side of R to another, and also with so-called T-junctions, so lines that just kind of start at one point and finish at some other point inside of the rectangle R. They don't necessarily end at its sides at all. Awesome. So that's the rectangle R. I forgot to label it. Okay, nice. So now I would like to see one thing. We actually have the partition using vertical and horizontal lines. So see, we have, this is the partition to the side of us. So we have horizontal lines here, 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 something like this. We also have, those are vertical lines. So vertical lines here, 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 and we have also horizontal lines here and here. So, well, we would like to now call the lowest line, horizontal line, as H. We would like to call it H. Awesome. And I would like to call everything that is above H R prime. Yeah. I will only focus on stuff that is here inside of the rectangle that is created by the bottom side of R and H. So everything that is below the line called H. Perfect. So now we see here that we are actually given some, let's say, blocks of rectangles. So that's, for example, a block of rectangles. That's another block of rectangles, and that's a third block of rectangles in this particular case. So those blocks of rectangles are created in such a way that the borders are either the sides of R or those lines or those vertical lines that go from one side of R to another. Yeah, and those borders of rectangles inside of those blocks are usually just always just T-junctions, or maybe they are known so that there is only one rectangle in and the entire block. So a block is actually a rectangle in itself. Lovely. So what does it mean? Well, this is just a particular case we draw here, but we would like to make it applied. We would like to make it applicable to all of the cases. So we would like to say that they're gonna be, let's say, R blocks. And we'd like to know how many rectangles there are in each block. So let's say that there are Ki rectangles in the ith block. That makes pretty much all the sense here. So now we would like to know how many points there are gonna be in R prime when I also will do a little tweak here. So let's just right now say that there are some points that will lie here on those lines, on those vertical lines that will go to the other side of R. So the borders, those borders of blocks of rectangles here. We would like to move, those points above R, above H, yeah, into the R prime territory. So we can absolutely do that. We just have to make sure that they will not lie on a single line that is parallel to the sides of R. After this kind of transition, there is no problem in doing that. Yeah, awesome. So now I would like to know what is the boundary for the number of points that we have right now after this transition in R prime. Yeah. So well, by the inductive assumption, we know that in every single rectangle where there are K rectangles, we have K minus 1 at most points. Yeah. So what is the number of rectangles in this particular case? Well, that's gonna be K. So the number of rectangles they were in the original rectangle R minus all of the well, I can't really write the sigma sign, now it's a little bit better, all of the rectangles that are here, so below H. Awesome. Now we're gonna just subtract that one from here. Those are the same ones. Yeah, awesome. So now people are going to school this way. I'm occupying this territory. Okay, so now we got this thing, and now we just have to also count all of those rectangles that were created by, you know, moving those points up those lines. So that's gonna be the sum. Oh, I really can't write sigma. From I, which is equal to 1 up to n, from ki minus 1 and also plus 1. The nice thing is that those two here will actually cancel each other out pretty nicely, and what we're gonna be left with is that this entire expression right there is equal to k minus r. And well, since r can't really be less than or equal to 1, well, r has to be greater than or equal to 1, is at least 1, what we are given is that the number of all of the points in R prime is at least k minus 1. So n is greater than, oh sorry, n is less than or equal to n minus 1. And so k is greater than or equal n plus 1, and that's exactly what we were supposed to prove in this problem using induction. Okay guys, so thank you very much for watching. If you enjoyed this one, then maybe, you know, consider subscribing or something, because then you will not miss out the future videos I'm putting out there. And well, if you did enjoy it, I am, well, delighted. See you in the next one.